And I'll just say real quickly that we are retesting on Tuesday for the test I just handed back to you from last time. And then most likely Thursday will be the other one. But make sure in the next couple of days you study for this one. I may do a half test for the other material on Tuesday too, and a half test on Thursday, so we can get some lecture in it. So, okay, so anyways. All right. So we were talking about substitution reactions. This is the SN2 reaction. Remember we talked about this being a bimolecular reaction, or SN2. Oh, it's not working. Hello. Not sure why it's not. Oh, well, I don't know why it's not writing S. Oh, my pen is not paired. That is weird. I'm gonna do this. Let's see if that works. There we go. Okay, it said plug it back in. So that's an SN2 reaction. The rate determining step, the slowest part of the reaction, involves two molecules coming together. Okay, and that was the demo we did here, Brett and I. Brett was, of course, the fast molecule. I was the slow molecule. Anyways. But that was SN2. But he had to wait for me, and that was the whole idea. And then as these things come together, right, the energy begins to go up. And then because of sterics, right, strain, as this OH group comes in, it has negative charge, so all these bonds have to move out of the way. So the molecule, just like if you were holding an umbrella in the rain, right, and the wind, like yesterday, the wind just would blow behind you, and the umbrella just pops out like that. That's what this is doing. So this is called an inversion. We talked about that's called a Walden inversion last time. Now, at this point here, we're at the very highest energy of the reaction, and it can either go back to the reactants or continue on towards the products. Okay, everybody has their slides, right? I handed them out. Yeah. So from that point, it can go to the right or the left, and we call this. This is again the Walden inversion. This is the peak of it. This is known as the transition state, because it's the transition between the reactants and the products, okay? Okay, so then it completely inverts, and you end up with your product, and in your product, we would say that this is inverted. Now, it doesn't always matter that it's inverted, but remember we talked about stereochemistry and the geometry of the shape of a molecule. If you do this to a molecule that has stereochemistry, its stereochemistry inverts because the molecule flips over. Okay? It inverts because it flips over like that. Okay, so the overall energy diagram looks like this. There's one transition state and a reactant and a product. So as far as stereochemistry goes, right, when this reaction happens, and this is a little bit hard to see because it is two-dimensional. I'll go get the model kit, maybe that'll help. This comes in. Now, if the BR is in the front like this, right, where does the OH have to come in from for it to properly react? It has to come from the back. It has to sneak around because remember the way we did that drawing before, right? There's a molecule that's like this, and then a nucleophile comes in and hits this thing, and then these flip over to the other side. So in order for this OH to get connected to the carbon right here, it has to come from the other side. The other reason why, though, just simple reason why, is if it tries to come in from this side, what's it go run into? It'll connect to the BR, right? Yeah. So remember also the reason why the OH goes to the back is this thing has a negative charge, and this thing has a partial positive charge over here. So it'll come around like this, come from behind, and attack at that carbon. Okay, and then when it does that, the BR leaves. Now, when you do that, this is the configuration of the molecule that you get. And if you look at its configuration, right, it's S versus R, it's flipped over because the molecule flipped over. Okay? So you guys remember R and S? Yeah? It's flipped, it's inverted. We say it's inverted the stereocenter. That's what we say. So that's what this term, this is how we actually refer to it. Stereocenter is inverted. Now, if it's not a stereocenter, doesn't matter. It's still, the reaction still happens the same way, but you don't have a stereochemistry to keep track of. All right, questions about this? This is stereospecific. So if you have S at the beginning, you'll end 100% S molecule. At the end, you'll have 100% R. So you get exactly the opposite if this reaction happens. Okay, so a couple of things about SN2, right? It's fastest for methyl and primary. Fastest for SN2. So here's sort of a general reason why. Let me darken this up a little bit. I really wish they would have given us independent light controls for the front. I need to tell the builders that for the next building. We need 2 light switches, one so you just kill the lights in the very front. I hate turning the whole lights off in the whole room. Okay, so general reason why this is the fastest and this is the second fastest is because as you put more groups, so this guy is CH3, that looks like BR. This is CH3CH2BR. And this is CH3 like that, and then BR. And this is T-butyl bromide. It's a C with CH3s all the way around it. Like that. Okay? So that's what those structures are that are being represented right here. Now, the reason why, like, for tertiary, remember this is a tertiary alkyl halide, this reaction is the slowest, is because there's so much steric strain around the site where the nucleophile comes in, right? So think about it like this, you know, you're walking down a dark alley by yourself, you're gonna get mugged, right? But if you walk down the dark alley and you got your 3 friends behind them, maybe one of them gets mugged, but you don't get mugged because you got all your friends behind you, right? Or you can think of it as if you're swimming away from a shark in the water. If you're swimming by yourself, the shark will eat you. But if you have your 2 buddies behind you, yeah, you'll get one of them, not you. I don't know if that works for you or not, but hey, ask them what happened, but I didn't finish grading it. I'm handing it back. We're gonna retest on it. Okay. Yeah, yours was not super horrible, but it was a lot worse than you're used to. So I just realized at this point, I got through a couple of pages and I thought, I'm stopping. Okay, so that's the idea. So here's another thought. Okay, when you're looking at this reaction mechanism, the SN2 reaction mechanism, it's really easy to do it on methyl and primary alkyl halides. It's a little bit slower at secondary alkyl halides. It's so slow, in fact, on tertiary alkyl halides, it's hard to measure. Like, it's so slow that you could wait days and days and days and days and measure very little SN2 alcohol, okay? And most of the time it's an artifact from something else. So, yeah, this is so slow that essentially SN2 does not happen on tertiary alkyl halides. Another thing that affects the SN2 reaction, and it affects lots of reactions actually, is the nature of the leaving group. And the leaving groups that are the weaker bases are the best leaving groups. Okay? Weakest base is the best leaving group. Now, do you remember why HI is a stronger acid than like HF? guys remember why HI is better than HF? It's stronger acid. All right, so if I asked you the question, just like generally speaking, like why is, I did right, okay, HI stronger than HF. Stronger acid, I should say. It's not got muscles or anything, but yeah. So, why is HI a stronger acid than HF? You guys remember? It's because it's larger. And what does that do? What's that? It allows the electrons to spread out more, yeah, right? And that's the same reason for resonance. Like resonance makes acid stronger because it allows the charge to spread out, right? Oh, which by the way, on that test, just 7 was the bad question. There was no right answer, so make sure you scratch that out. But in general, resonance makes acid stronger because it delocalizes electrons. So HI is a stronger acid than HF because I minus is more stable. And so it actually is a better leaving group for the same reason. It's a large negatively charged ion. That charge is dispersed across the surface. So it is a much weaker base because of that, and also a better leaving group. Oh yeah. Forgot I got this t-shirt on. All right. Okay, now the other thing that affects SN2 reactions is the nucleophile. So here's a couple things. Negatively charged nucleophiles are always better than neutrally charged nucleophiles. So if you have a choice between using OH minus and H2O, right? OH minus will be a better nucleophile. You'll get the same product if it's an SN2 reaction, but because of the negative charge, it's just better at attacking. Okay? Also, stronger bases are better nucleophiles. Okay? Stronger bases are better nucleophiles. Now, saying that, right, this is a stronger base than this is a stronger base than that, so this would be the best nucleophile, this is the worst nucleophile. That is, if it's an SN2 reaction, you look at acid and base strength, and you could determine which one's a better nucleophile. There's actually a third thing. I'm not going to test you on it, but it actually turns out atoms with larger orbitals, it's not in your book, are better nucleophiles as well. In essence, when you want to form a bond, if you have a bigger orbital to form a bond with, it just forms better. It's just easier to do. We're not going to deal with any of that in this chapter, though, for sure. So questions? Okay. So SN1 reaction. So in an SN1 reaction, if you remember us talking about this before, it only depends on the concentration of one of the reactants. The other reactant doesn't matter. That would have been Brett, doesn't matter in that example. I was the one going slow, and I had to do something, and then he followed after me and did something else, right? So there's a two-step reaction for an SN1. And we call it SN1 because it only depends on the concentration of the substrate. And because it only depends on the concentration of the substrate, we call it a unimolecular reaction. It's a one-molecule dependent reaction. Okay? All right, so let's talk about the mechanism real quick. And I'll just draw it on here. So in the first step of the mechanism, this bond has to break. I'm going to draw this one out. And what you're going to form is this. Okay. So this is how we draw the mechanism. Like in SN2, it's one step, so it's one arrow in, one arrow out, and you have your product. Okay. There's an inversion and all that. But in this step, what did we just do? We broke this bond, right? This is the slowest step in the reaction. And it's slow because you have to break the bond, so that requires the most energy. Everything that follows after that is fast, relatively speaking. Now, I'm going to compress this a little bit, but the rate of the reaction, okay, I'll just call it reaction rate, depends on how fast you can form the carbocation. If you remember, right, carbocation has a positive charge on it, right? And in turn, right, how fast you can form the carbocation is dependent on how stable the carbocation is. Okay, what did we learn about carbocation stabilities before? What's the most stable carbocation? What's the least stable carbocation? Do you remember? Yeah, tertiary is the most stable because it has the most alkyl groups around it. So that's actually why this is drawn with the tertiary alkyl halide, because that's the one that forms the carbocation easiest. This is where we see it the most. Okay, so we know that tertiary is more stable than secondary, which is more stable than primary. So this is more stable, and it also means faster, SN1. And then below this is methyl. Okay. I don't know if you can read that or not. So it depends on carbocation stability, right? Tertiary is the most stable, and so it gives us the faster SN1 reaction rate. That's kind of interesting because tertiary alkyl halides were also the slowest SN2 reaction rate. So you know that if you have a tertiary alkyl halide, it will only go by SN1 reaction rate. So that's the only way it forms a product. Now, let's think about the carbocation, right? What's its hybridization? Do you guys remember how to do it? How many groups does it have? 3. What is it? SP2, right? And it has one p orbital left over, right? Remember the whole finger thing. So that means it's SP2, it's planar. It's basically it's flat, right? So at this point here, after the carbocation is formed, like here, right, the nucleophile comes in and forms a bond. So the OH minus will come in and attack the carbocation, and that'll form the new bond. So let me redraw that step over here. So I have CH3, C plus, CH3, CH3, and then the OH minus comes in and attacks, and then you end up with your product. Okay? That'll give us the product. But now, think about it. If the carbocation is flat, and then you have these hydroxide groups coming in to attack it, right? It could attack from either the front or the back. So if you have a stereochemistry at this carbocation, it goes away in an SN1 mechanism. It becomes racemic. You'll end up with two different stereoisomers. That makes sense? The intermediate is flat, and so because it's flat, the OH can either come in from this side or it can come in from this side, and you end up with two different products potentially. Now on this one, because every group around it's a methyl, it doesn't matter, it's just one product. Okay? But if you have a stereochemistry, it'll make a difference. Energy profile for this thing looks like this, right? The hardest part is to stretch this bond out, and when it breaks, right, it's going to have to go over this hump. Sorry, it'll have to go over the energy hump that's up here. And then when you form the carbocation, that's right in here. Now, depending on whether or not the carbocation is more or less stable, right, more stable makes this go down, and less stable makes it go up. Like I said, the intermediate is, that's what's in the saddle of the energy diagram. The intermediate is flat, and it has this p orbital on it. And when the nucleophile comes in, right, it could either come in from the top side or the bottom side. So the nucleophile could either come in from here or it could come in from here. And when you do that, you get two different products out. Okay, so I have it coming in from the top here. There's a reorganization or rehybridization of the molecule, and as that bond begins to form, right, you eventually will completely form this bond, and the energy will be towards the product side. So just quickly going through those, what's going on, right? Bond stretches, carbocation forms, nucleophile comes in, and then you end up with your product. All right. Yeah, so the energy looks like this. The energy diagram looks like this for the reaction. It's a two-step reaction. This is where the intermediate is. I'm not going to ask you a lot of questions about these diagrams. I just want you to get the idea of what's going on in terms of energy. But if you can make this energy go lower, that allows the reaction to go faster. Because you have two peaks on it, you end up having what's called two transition states. Two transitions where it can go forwards or backwards. Okay?
Is the second one always lower in energy than the first one?
Generally speaking, because if it was more energy, it would actually be the slower step. Right? So if the second step has to generally be less, and this reaction has to be less than the first. I think I gave the analogy at some point about running hurdles. And if I was down a race, I don't know if I ever told this class that. Like the activation energy barrier, the hump, right? The bigger the hump is, the slower the reaction goes. And it's like running hurdles. If you're running hurdles on like the grown-up hurdles, it's really slow. I don't know, maybe you're a runner, but I'm not. But if you go on the little kiddie hurdles that are like 2 feet tall, I think most adults could reasonably manage that. I'm not one of them, but most of the adults can reasonably manage going over a 2-foot hurdle. Right? Well, I could if I stopped and then stepped over it. I think I'm past the days of trying to sprint. All right, so part of the consequences of the way this reaction runs, it only depends on the substrate concentration, because when the nucleophile comes in, right, that step's a lot faster, lower in energy than breaking that bond. That I do want you to remember, by the way. The breaking of the bond is the slowest step. Okay, so try to remember that. The rate depends only on the formation of the carbocation. And then the intermediate, another thing I want you to remember is trigonal planar. It's sp2. And actually the other thing, which is on later slides, but I sort of shortcutted all of it, is because the intermediate is trigonal planar, you lose any stereochemistry you might have had in the molecule because it flattens out, and the nucleophile can come from the top or the bottom. So I do want you to remember that if there's stereochemistry, there's a loss of any stereochemistry. It becomes racemic. If you remember the term racemic, it means you have equal amounts of R and S in the product. Turns out that's not 100% true. There's some other funny things that can go on, but for this class, yeah, it's true 100% of the time. All right. Yeah, so just some examples. Let's say you have this molecule. This is where the Br is. This is tertiary, right? So you'll need to know that if it's tertiary, the only mechanism it can go through is an SN1. So this bond will break and you'll get a carbocation here. And now the OH can either come in from the front or from the back. Right? When it does that, you'll end up with two different molecules, one with the OH going forward and one with the OH going back. Okay? Now these will have different RS configurations. In fact, let's try to figure out what the RS configuration is. What's the number one group? Let's do the RS for this guy. We'll call this guy A. So for A, right, what's the lowest priority group? That's the easiest one right now. Huh? Hydrogen? Yeah, but there's no hydrogen on there, right?
On the OH.
Well, there is. Oh, no, but we're trying to figure out this stereochemistry.
Oh.
Right. Okay, so the lowest priority group on this is.
Well, isn't the hydrogen the one that goes toward us?
Huh? This is coming towards you, or back, right? It's going back. But this is not hydrogen. This is a CH3 group.
Yeah.
Right, yeah. So this is the lowest priority. They just didn't draw CH3 in. So this is CH3, so that's number 4. So this is number 4. That was weird. What's number 1? OH, yeah. Highest atomic number. And then, so this is 4 here. What's number 2? Well, this is how you have to do it, right? You look at this point and this point, and you're comparing, right? And they're exactly the same at that point. And then you go to this point, and you go to this point, all right? And this carbon that's down here, right, this guy here, he has a bunch of carbons attached to it, all right? It's quaternary carbon. So what that does make it is the higher priority is going down. So this is number 2. So that would be 3 here. So it's going like this. But the number 4 group is in the front, right? So this is just review. This is, looks like it's R, right? It appears as R. But 4 is forward. And remember, all of these are done with 4 being in the back. So if you flipped it around, everything would flip around. So it's actually, this one's actually S. This one looks a lot the same, right? But again, this is 4. This is 1. This is 2. It's going this way. Now 4 is in the back, right? So this is actually R. Okay. But again, you need to assign priorities, determine the direction of clockwise, counterclockwise, and then look to see where 4 is at, front or back. So, yeah, so you get a pair of distereomers. Oh no, yeah, these are distereomers because of this center over here, I think. No, it's actually a pair of enantiomers. You get a pair of enantiomers out of this. Okay. Oh yeah, and you'll get equal amounts. So this is known as a racemic mixture
Will
of
they
R.
always come out as enantiomers?
Huh?
In this type of reaction? Will they
Yeah,
always come
so
out?
these are enantiomers. Now, if this doesn't actually have stereochemistry, I tricked myself. I looked at the wedges. It's just they're showing one in the front and the back. But if this had a bromine here or something else, or some other functional group like an OH, then what would have happened is this center wouldn't have changed because there's no reaction, but this one would be R and S, and so it would end up being distereomers in that case. Like, remember, distereomers are the stereoisomers that aren't mirror images of each other. Because these are both methyls, they turn out to be mirror images of each other. That makes sense, sort of?
Mm-hmm.
Yeah. Okay. Okay, so what makes SN1 go? Well, carbocation stability is, like I said, is the most important thing. Just like SN2 reactions, iodide is a better leaving group, so it also makes it faster. Okay, so the leaving group effect is the same for SN1 and SN2. The better the leaving group, right, the better the reaction goes. And for the nucleophile has no effect. So if you change the concentration of a nucleophile and the reaction rate doesn't change, it's SN1. Okay? So what no effect means is if the concentration of the nucleophile is changed, there is no effect on reaction rate. In fact, you could even just change the nucleophile to something completely different and the reaction still goes at the same rate. It just depends on how fast that carbocation forms. It's a hard idea because you usually taught, well, if you change something there should be a change, but in this case you change something, there's no change. And the SN1 reactions at tertiary alkyl halides are all very, 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 very fast. They all happen at room temperature within seconds. Like, you mix the stuff together and it just like, it's done. Which makes for great labs in organic chemistry, because literally the students come in and they mix two solutions together and they shake it, and the rest of the time they spend separating, but the reaction's done in like 10 seconds. They're like, is this all I do? I'm like, yep, that's all you do. All right. Comparison between SN1 and SN2. And this is what confuses students. I just want to make sure I point this out. It's SN2, and it's a one-step mechanism. It happens in one step. Right? Because the 2 means the reaction happens when both molecules come together. And when they both come together at the same time, you get the product out right away. So SN2 is bimolecular. SN1 is 2 steps, because remember, just like we were over here, first guy had to do something, then the second guy had to do something, right? And so the first reaction has to do something, and then the second reaction has to do something, but it's only dependent on how fast that first guy goes. Now, in SN2 reactions, you'll get the inversion of the configuration. So if it's a stereocenter, its inversion flips over, and that's 100%. Like, we call it stereospecific. There's only one outcome to the reaction. And then in SN1, it ends up being racemic. That means you get a mixture of R and S. So you could start out with all R, and you do an SN1 reaction, and it's R and S at the end. Okay? And the final thing is the reactivity order. This is not supposed to be bulleted. It's just underneath. Methyl is the fastest for SN2, then primary, secondary, and so slow that you might as well just go like this on SN2. It just doesn't exist. It's so slow. And it turns out it's the opposite for SN1. And in fact, it turns out these don't exist. So if I ask you if a reaction looks like it's going to be an SN1 mechanism, all you need to do is look at the substrate. If it's tertiary or secondary, it can be SN1. If it's only SN1, it has to be tertiary. Right? This is only SN1 because it doesn't happen here. Here could be SN2, but only SN2 because it doesn't happen on SN1 doesn't happen on primary or methyl carbocations. So it's just too unstable to be formed. Okay, let's see, what's the next slide? I forgot. Oh yeah. I should probably look at my slides while I do this. So in trying to help you decipher some of this, I do want you to be able to do this part. I'm not sure it's in the book, but it's if you're given the option of SN1 and SN2, okay? Well, SN1, if it's tertiary, that's all it is. It's SN1. You don't have to think beyond what the substrate is. If it's a primary substrate or a methyl substrate, it's only SN2. So you don't have to think about the nucleophile or anything. Those are the only options you have. So what does that mean? It means that secondary substrates, you have both SN1 and SN2, and you have to have something to help you decide which way it goes. Okay, so back up for a second. I'm going to go back to the slide before. Right, the SN2, I'm going to put a little note here, depends on the nucleophile. And I'm just going to abbreviate it as a capital N. And then in SN1, it doesn't depend on, D goes the other way. Okay, so for SN2, it depends on your nucleophile. For SN1, it doesn't. And so that actually helps you decide like whether or not it's going to be SN1 or SN2, because if you have a good nucleophile, negative charge, right? Or it's large, that's the other thing you don't need to know that for this class, if it's a large molecule. But if it's a good nucleophile, then it'll be SN2. If it's a bad nucleophile, so if it's neutrally charged, like water versus OH minus. OH minus, SN2. Water, SN1. And then solvent also has an effect, and I'm going to tell you, you need to know this, but it's not in your book, okay? But the solvent also has an effect, and if it's hydrogen bonding, it favors SN1. And let me just tell you what it means to be a hydrogen bonding solvent. Like H2O, hydrogen bonding. You remember what a hydrogen bond is? You have to have oxygen, nitrogen, or fluorine bonded to hydrogen. So H2O is a common example. NH3 is a common example. It means something with a nitrogen in it. These are all hydrogen bonding. We don't use HF, like hydrofluoric acid, as a reagent. It's like too nasty. But so you only really have to look for oxygen or nitrogen in the solvent, and if the solvent is hydrogen bonding, it favors SN1. Okay, that's all you have to remember. It's cool the reason why, though. I can't not talk about it. If you're hydrogen bonding, right, and you see a nucleophile, like nucleophiles have a negative charge, right, and lone pairs of electrons. So if you're hydrogen bonding, solve it, and you see a nucleophile, you just grab onto it and don't let go. And so even though the nucleophile wants to react, the solvent won't let it, because it's like you're going to a party and you're the most popular guy in the room, and well, I don't have this experience, but if you're the most popular guy in the room and you walk into the room, everybody surrounds you. So you're the nucleophile and you want to go to meet with your electrophile. It's hard for you to get together with your electrophile because everybody keeps you from getting there, right? But then if you're not so popular, right, or the solvent in the room is not hydrogen bonding, right? And you're the nucleophile, and there's the electrophile. You walk into the room, and nobody cares you came in, so you just walk right up to your electrophile, do whatever you do, right? But you can react at that point, right? But you can't react if the solvent like surrounds you and keeps you from getting there. So it is pretty like, okay, I relate everything to dating and all that stuff. But yeah, it is kind of interesting how that has an effect. Hydrogen bonding solvents tend to swamp the nucleophile. All right, next kind of reaction. Oh my gosh, we might actually finish this chapter. Elimination reaction. So elimination reaction is for an alkyl halide, right? So X represents Cl minus usually, or Br minus, or I minus. It's not usually F minus, okay? But in an elimination reaction, you form a double bond, and you eliminate a small molecule. So it doesn't have to be an alkyl halide when you do an elimination reaction, but in this case, it'll be some sort of acid that is eliminated. So this is the small molecule. And then you get a pi bond. Okay. So those are the characteristics of an elimination reaction. You have a leaving group on a molecule, you form a double bond and another small molecule. We usually don't care about this guy, we just care about the organic part. Okay. Generally speaking, right, if you look at this, OH minus is a good nucleophile. So this could be SN2 because that's a primary alkyl halide. This could be SN2 because it's a good nucleophile and a secondary alkyl halide. Now if it's tertiary, it can't be, right? So good nucleophile, alkyl halide, looks like substitution. The only thing that makes it different is you heat it. If you add heat to this, right, that forces the reaction from being a substitution reaction into being an elimination reaction. The small molecule that comes out of here are these guys. Now we'll go over the mechanism for it in a little bit, but yeah, you remove water, and it kind of helps to you think about it, that fact that you're eliminating a water molecule, because you think when you heat up a solution, right, it tends to drive the water out of it, and so by driving the water out of it, you end up getting elimination products. So these reactions are tricky in the sense that they look like they could be substitutions, but because of the triangle, this means heat, okay? I don't know if you guys know that or not, actually. That means you heat it up, you get elimination instead, okay? Let me do something really quick. I think I'll go over the mechanism real quickly right now, just to help you guys out with this. So let's say I have this. Oh, actually, I want to draw these out. Okay. So this is my alkyl halide. It's actually the one that was on the previous slide. It's just, this is all drawn out. Now I'm going to bring in a strong base. So this is OH minus as a strong base. What happens in this reaction? There's actually two ways the reaction can take place. principally what happens, though, in this reaction is this grabs that. It's like an acid-base reaction where you have a base and then you find an acid. This hydrogen, it turns out, I can't even reach that high. This hydrogen over here turns out to be slightly acidic because it can be pulled off by the base, and when it does that, it's going to do this. So this all happens in one step. Okay. So this is an elimination reaction. When you do that, you're going to get this. There is a question I'm hoping somebody asks. You're saying to yourself, but why doesn't you probably have the right question in mind. So that's one possibility, it turns out. Right. And then that would be your alkene that you get in elimination. This is often known as a beta elimination. So how many of you know, like, the Greek alphabet? What's the first letter in the Greek alphabet?
Alpha.
Alpha. What's the second?
Beta.
That's all you need to know. So, first is alpha, beta, is gamma, epsilon. You know, it's like there's a delta, epsilon, delta, delta, epsilon. Yeah, so anyways, but it doesn't, you know, when you sing the ABC song in Greek, it doesn't sound as good. Can you imagine doing that? Alpha, beta, A, B. I don't know, that would be hard to do. I should just write it up so people can learn it, but then it doesn't have the same number of letters, I think, and so then you have to like be like, I don't know what you sing here, but this is a different letter. It's in the wrong order. Zeta, it's set C, or some other weird. Sorry. Yeah. So alpha, beta. So here's what alpha is. Alpha is the carbon that the functional group is attached to. Okay. So in this case, the alkyl halide. Alpha is the first carbon. Beta is the second carbon. So this is my beta carbon. And when you do a beta elimination, you take the alkyl halide off and the hydrogen off a beta carbon off, and you form a double bond.
And it's the beta because it has the most hydrogen attached to it?
No, because it's next to alpha. So, you know, like in the order of the alphabet song, alpha, yeah. So why did you say that?
Because
there's another beta. So there's two products. That was the thing I was hoping somebody would say. This is also beta. Right. So because you have two betas, you have two possible products. So the other possible product is to remove this hydrogen, and when you do that, you'll end up with this. So you end up with a double bond in the middle. Okay. And actually, there's three possible products because this could be cis or trans. So let me point out to you something. This this is part of what's known, I'm about to tell you, is part of what's known as Zaitsev's rule, okay? You remember how there's Markovnikov's rule for addition? You always form the more stable carbocation or the more substituted, right, carbocation. So Zaitsev was, again, I think about a contemporary of Markovnikov. And Zaitsev basically said, you do a beta elimination to form the most stable double bond. But it turns out that means the more substituted double bond. Okay. So, strong base comes in. I have three possible products, right? Most likely, you're going to get this one. Because Zaitsev says it's the more substituted double bond, and the more substituted double bond is the one that has the fewest hydrogens on it. Has more carbons on it. Okay? This one only has one carbon on it. This guy over here, he only has one carbon on the double bond. The rest are hydrogens. And then here you have two carbons. You have one on this side, and then you have one on this side. So what Zaitsev's rule would say then is this is the double bond that you would get. And on top of all that, trans has got less steric strain to it, so you most likely get a trans double bond. Okay? So that'll be your major product out of this whole reaction. But yeah, we follow something called Zaitsev's rule, and it has to do with the degree of substitution of the double bond. More substitution, more stable. So again, just to reiterate, this is actually on the next slide. You have an alpha carbon and you have a beta carbon, and when you do the elimination, you get rid of the halogen on the alpha and the hydrogen on the beta and form a double bond between those two carbons.
Do we use only water with chlorine and
Yeah, so if you do H2O and you have the alkyl halide and you heat it really strongly, you can get an elimination reaction still. The mechanism's a little bit different, but not that different. I could draw it out for you if you want me to. Hang on. I'll draw it on the bottom of this slide. So I'm going to do it in a line drawing format because it's just a little easier to do. So there's my alkyl halide, right? This is the same molecules in the last. There's a hydrogen here, and there's a hydrogen here. So this is not what people would do because it's not the best way to do it because because it's not a very strong. Is this what you're asking?
I think I figured it out.
Okay.
Confused.
Okay. Yeah. So, but it could still be done. It would be exactly the same. This is the same mechanism. But instead, you would end up with H3O plus and Cl minus over here. You would still end up with that as your major product. Okay. So, beta elimination. Yeah, so again, a base comes in. Now, the base is also a nucleophile. The only thing that's making this different is the aspect that you're heating it. Heating it at the strong base will most likely give you an elimination reaction with less substitution. If you don't heat it, it turns out you get a mixture of substitution and elimination. What happens when there's more, right? That's exactly what we were covering just now. Right, we follow something called Zaitsev's rule. We say that the reaction in this case is regioselective. Which one of those is going to be the major product, right? Is the elimination of the hydrogen here rather than the hydrogen here because there's more substitution in the product when you eliminate there. So in other words, you can form two products. If you have two betas, you just look at that versus that, and you decide whether or not the double bond is going to be more or less substituted, right? The major product, they say, is the one with the lowest energy, but the major product, like I said in Zaitsev's rule, is the double bond that would end up with the most carbons on it. And like I said, also for the 2-butene, it could be cis or trans, and most of it will be trans. Another example, there's actually three possible, you can have three beta hydrogens, right? So there's three possible double bonds that you can form here, right? Again, OCH3 minus is a strong base, and it's heated, right? And then you can eliminate either this hydrogen, or that hydrogen. It turns out when you eliminate from here, or you eliminate from here, this product is the same as that product. That's why it says beta prime is equal to beta. And then this one is the minor product. And there's always some mixture of products when you do this. We say it's regioselective, right? Because it prefers one region versus another. That is, it prefers to form a double bond here over here. I always tell students, you're all regioselective too, because you're going to go to school and get a degree, and then you're going to kind of try to choose where you live, right? It's the same thing. That's all that means. You're going to choose where the double bond is based on stability. You're going to choose where you live based on stability, right? Why am I Reedley? Because I've lived in the Bay Area, I've lived in Iowa, I lived in Indiana, I lived in North Carolina. Yeah, I think that's it. And Reedley, right? Because this is where I'm the most stable. I have family, I have a job. Job's important. Right? But I could have had this job just about anywhere, but I chose to come back to the valley. Okay, so alkyl halides with a weak base. The beta hydrogen removal is harder. And so what happens is you get different mechanisms. It's called an E1 mechanism. Okay. There's not much to say about an E1 mechanism other than it's just like the SN1 mechanism. The slow step is the carbocation forming, and then the second step is the elimination. So in the E1 mechanism, this bond has to break. That's the slow step. And that's one of the reasons why I like to talk about E1, because it's just like SN1. You don't have a good base or nucleophile present. You have water or an alcohol present. But once you form the carbocation, and there's a lot of information on this slide. Once you form the carbocation, the formation of the carbocation, right, goes based on tertiary, secondary, primary. Tertiary is the fastest forming, primary is the slowest forming. And then you get a beta elimination. That is, the base, whatever the base is, comes in, grabs that hydrogen, that pushes those electrons back to there, and you form your double bond. There's a little note here. It says works best in polar solvents, which is just because ions are more stable in polar solvents. Questions about E1? Carbocation, then elimination. But it's still a beta elimination. Still the other hydrogen has to go. Still follows Zaitsev's rule. Still follows the same stability rule. Most substituted double bond is the one that's formed. Yeah, we don't need to know that part. Let's see. Yeah, again, E1, just like E2, you get your major product is your more substituted one, and your minor product is your less substituted one. So it looks exactly the same. Now, I will tell you, like, if you take this again, I know there's a handful of you that might take another organic chemistry class. There's more to the E2 reaction that involves stereochemistry. We don't care in this class. I just want you to know E1, E2 give roughly the same products. That's it. There's a little bit of reading at the end that I'm not testing on. You remember on the first slide I said, right? I don't know if you remember that. Like on the first slide I said problems 1 through 22. I'm only testing through section 8. There's like 10 sections. I didn't lecture on the last 2, but I assigned some problems for you to look at. It's more for you to have exposure to that material. It's part of like what we're supposed to teach you. So you're just going to teach yourself, and I'm just going to call it good. I recorded that, I think, yeah. I have evidence, I told you that. Any questions?